All right, so then welcome everyone to this little logic workshop that we're going to be having here today. And our first speaker for the day, so we're going to have 4 speakers in the morning, well, the morning after, or like midday. We are going to have Pablo Cobreros from the University of Navarra as the first speaker. Then we will have Sara Lapenta from the University of Salerno as the second speaker. We will take 30 minutes lunch break or something like this. And then in the afternoon, we are going to be back with Dave Ripley from Monash and Alba Cuenca from Monash as well, like for the afternoon session. So with that said, Pablo is a professor at the University of Navarra. He's visiting here for a couple of days. And he's going to be speaking to us about trees in the Smoolian style for non-classical logic. So please, Pablo, take it away.
Thank you very much, Guillermo. Paso desde aquí, ¿verdad?
Exacto, sí. A ver, yeah, perfect.
Okay, so thank you very much for your kind invitation. And well, in this morning session, I want to talk about a small book, introductory book to non-classical logics that I'm writing in Spanish. I thought that this was a good idea because there is a growing community of Spanish-speaking logicians. And as far as I can tell, there is no book of this sort, though you can find many nice introductions of this sort. In English, I think it's time to try to make something in Spanish. So this is my little grain of salt. So everything I'm going to say is rather basic. I'm sorry, but this has one advantage, and it is that things can only improve in the day. So, okay. So the topic that gives unity to the book is the use of Smalian trees, and one of the goals is showing the user-friendliness and versatility of this method to handle different themes in philosophical logic. The method of trees allows us to extract the proof theory out of a semantic characterization of a logic, and although sometimes these kind of proofs are regarded as impure in the sense that they usually contain semantic vocabulary and expressions that are not part of the language. So I think that they are, in any case, worth studying, because even if impure, these trees usually give you like a middle ground between a semantic theory and a proper proof theory. And normally they help you to get some insights on the nature of a particular logic, and often raise non-trivial questions on proof theory. So let's start with a brief overview of the method. So basically, you have a semantic definition of logical consequence, and this usually goes with a definition of that an argument is valid just in case there is no counterexample to that argument, where a counterexample is a valuation that sets all the premises into a set of good values, let's say, and all the conclusions into a set of bad values. Now, a tree proof will depart from an initial list, assuming, so the initial list will tell you that there is such a counterexample. And of course, you can decorate this initial list with all sorts of things like semantic values, or perhaps some operators going with the formulas. The second step is, once we make our assumption of the existence of a counterexample, we'll have some tree rules allowing us to chop formulas into smaller pieces. So some of the tree rules will open a branch. In some trees, they might open more than 2 branches, actually. Some of the rules don't open a branch. And the idea is that these rules dig into the conditions that subformulas must fulfill in order for the formulas in the initial list get the right values, so to speak. And the chopping process guarantees that the search always works in the direction of formulas with lower complexity. So the idea of chopping is actually essential for the method is very much connected to the decidability of the method. In the chopping process, a branch might show a situation forbidden by the semantics. So the branch is telling you that you cannot follow this path in order to find your counterexample. And we usually record these conditions or situations forbidden by the semantics in a list of closing conditions. If every branch in the tree closes, this is telling you, the tree is telling you that there is no counterexample whatsoever. And so the argument is valid. So initial list, assume that there is a counterexample, tree rules, chop the formulas in the initial list into smaller pieces, closing conditions, detect situations forbidden by the semantics. Now, in the classical case, we have that an argument is valid just in case there is no two-value evaluation that sets all the premises taking value 1 and all the conclusions value 0. And in our initial list, we will write the formulas in the premises and the formulas in the conclusions. Instead of using tags, you can use negation, right? Because non-truth and falsity comes to the same thing in the classical case. And the tree rules have this shape. So some of the tree rules are like disjunctive truth conditions. So for example, A conditional B will branch and give you in one branch negation A, in the other branch B, while the negation of A conditional B is a non-branching rule and giving you A and negation B. And of course, the closing conditions is that whenever you have a formula and its negation in a branch, then that path is closed. So let's have a look to tree proof, showing that the classical conditional is transitive. So you have here A, negation A, so this branch closes. C, negation C, this branch closes. B, negation B, and the branch closes. So there is no counterexample. Okay, let's move now to strong cleanly trees. Here the idea is the basic idea is very simple. We can expand our semantics with a third truth value so that evaluation this time is a function from variables to the set of three truth values, 1, 1.5, and 0. We can give different interpretations to these to the connectives, but we are going to attach here to the strong cleanly scheme that gives you or interprets conjunction as the minimum, disjunction as the maximum, and negation flips 1 to 0, and the middle value to itself, and the conditional is read in the material way. We will say that a formula is strictly true when it takes value 1 in evaluation and tolerantly true when it takes value non-zero. Okay, now this time, the interesting thing of the third truth value is that it allows us to give more definitions of logical consequence than the classical semantics. A very traditional way of defining counterexamples is in the K3 or LP style. In the case of K3, the idea is that a logical consequence preserves value 1, right? So a counterexample is evaluation making all premises 1 and all conclusions not 1. A second way of defining logical consequences in the LP style, where a counterexample assigns all premises value non-zero and all conclusions value 0. But we have some more freedom if we look at counterexamples and not just preservation of some truth value. We could define these other two alternatives, which are usually called ST and TS. In the case of ST, a counterexample is evaluation assigning to all premises value 1 and all conclusions value 0. So the fact that the counterexample have this shape, leaving this value, this middle value, is going to guarantee in some sense that the resulting logical consequence is non-transitive. And we can define a logical consequence in the TS way, where a counterexample is evaluation assigning to all premises value non-zero and to all conclusions value non-1. And in the case of TS, the fact that the upset, and the downset of the counterexample overlap will guarantee that the consequence relation is not reflexive. Okay, well, this is going to be useful. It's going to be useful to notice that a formula is strictly true just in case its negation is not tolerantly true, because just with the tags for strict truth and tolerant truth, we are going to be able to characterize all these counterexamples. Okay, so let's look at the trees for strong linear, for these strong linear logics. So an argument is going to be xy valid, where xy can be either s or t. So an argument can be ss valid, or st valid, or ts valid. An argument is xy valid when all the premises take x value and all the conclusions take a value that is not y, right? But given the previous equivalence, we can characterize that all the conclusions don't take a y value is the same as the negation of the conclusions take the dual value, right? So for example, an argument is going to be ss valid just in case all the premises take value s and the negation of the conclusions take value t, right? And well, the same goes for the others. The three rules are particularly simple and they look exactly like the classical rules, but with the difference that we will have to move the tag with the formulas. So if here we have an S, then here we have an S. If T, then T. And the closing conditions, so a branch is going to be closed when you have something like AX negation AY, but X and Y are not both equal to T. So in the particular case where you have a formula and its negation with the T tag, this branch is not going to close in this case. This is the case where the formula takes the middle value. In all the other cases, the branch will close. So let's go for some examples. Okay, so K3 is preservation of a strict truth, SS. So we depart from the assumption that the first and the second premise take the strict value, and the conclusion, the negation of the conclusion takes the tolerant value. Okay, we open, well, we chop this formula into these pieces. Now we chop this formula into these two other pieces. Here we have negation AS and AT, so this branch is going to close. We chop this formula to get these pieces here, and we have BS, negation BS, and negation CT and CS. So all the branches close. Now what happens if we look at the LP tree? Well, actually, all we have to do is just a relabeling of the tree. So in the case, if we have a K3 tree, in order to get the corresponding LP tree, we have just to relabel all the formulas and change SS by T. And what is going to happen is that in the K3 case, this branch closed with BS and negation BS. So this time in the LP tree, the branch is going to be open. And this shows that the conditional, material conditional, is not transitive in LP. In the case of ST, the funny thing is that you will only have S, the tag S in its formula. So that if a tree closes in the classical case, it will close in the ST case, which shows that ST is, so the inferences that are valid according to ST are exactly the classically valid inference. And in the case of TS, the funny thing is that all formulas go with T, so there are no closed trees for TS, right? So any branch of any tree in the case of TS is going to be open. Now, I would like to consider what happens with the case of meta-inferences. And why meta-inferences? Well, the reason meta-inferences, at least in this context, are interesting is that in the case of ST and TS, there might be more than meets the eye when you look at these logics, right? If you look only to the inferences of these logics, ST gives you classical logic, and you can say, hey, you have classical logic here. TS is empty, so no inference is valid. But actually, ST is classical in its inferences, but some meta-inferences that are classically valid are not ST valid. And similarly, in the case of TS, although TS is empty at the level of inferences, there are some meta-inferences that are TS valid. So TS is not completely empty. Now, how can we, we'll have to use some definitions in order to define a meta-inference validity. We will say that an inference is XY satisfied by an interpretation when either the premise is not X satisfied or the conclusion is Y satisfied. Here we're using single premise, single conclusion just for simplicity, but there is no difficulty on extending these definitions. And meta-inference satisfaction, evaluations, XY satisfies a meta-inference when either the premise is not XY satisfied or the conclusion, oh, sorry, this typo, or the conclusion is XY satisfied. And we will say that a meta-inference is valid just in case every evaluation is XY valid, just in case every evaluation XY satisfies that meta-inference. Now the question is how to extend the trees in order to cover not just inferences for a logic, but also meta-inferences. And here is a, I think, very simple and nice trick. We have to add to the trees nodes with inference form, right? So when we wanted to check for inferences, our initial list departed from formulas. Now that we want to check for meta-inferences, our initial list will be a list of inferences. So if we want to check whether A arrow B meta-inference arrow implies C arrow D, our initial list will contain something like A arrow B XY, C arrow D XY hat, meaning, of course, that the conclusion of the meta-inference is not satisfied. It's not XY satisfied. And the tree rules basically record the semantic definitions of inference satisfaction. So an inference A arrow B is XY satisfied. Well, that means that either A is not X satisfied, which is equivalent to the negation of A is UL X satisfied, or B is Y satisfied. And A arrow B is not XY satisfied exactly when A is X satisfied and B is not Y satisfied, right? And of course, this here was the initial list for our trees for inferences, showing that in fact we have that an inference validity is equivalent to a meta-inference without premises validity. Okay, and the closing conditions are basically the same. So let us look to some examples. Okay, this is a K3 example showing that a meta explosion or something like this is a K3 value. So we write the inference in the premise with SS, the inference in the conclusion with SS hat. Then we chop this into A is S satisfied and C is not S satisfied, which means negation C is T satisfied. Then we chop this thing into these two bits. This branch is closed and this branch is closed. Now, of course, in the case of LP, the relabeling will make this branch open. So in order to get the LP tree, we have just to change all the tags, basically. And since the K3 tree closes with SS, the LP tree is gonna be opened here. So LP is not explosive at the level of the dimensions. And in the case of ST, we get something very similar, not exactly the same tree, but we have that the tree is open. And in the case of TS, we have that the tree is closed. So, okay, I'm not gonna say much about this, but basically the same ideas that motivated the strong clinic case. Well, you can play either with the meaning of connectives, with let's say a weak clean reading of the connectives, but you can also expand the set of truth values to get different stuff. And all this is you can use the trees for all this. The only thing I want to notice is that in the case of the 4 truth values, we can have logics where the upset and the downset for the counterexample both overlap and don't exhaust the set of truth values, which will give you a logic that is both non-reflexive and non-transitive in some sense.
That finite set of values, can you do it with an infinite numbers of the values?
You mean for
Like a different logic in which you like
using you mean using the trees?
Yeah, this approach.
Yeah, it depends very much on the structure, and because in general, usually in order to get efficient tree rules, you will use, instead of tags for each truth value, tags for sets of truth values, right? So I suppose it depends very much on the particular case. My guess is that trees for the 4 truth values are already a bit messy. So if you include more, it's probably getting worse. And okay, so I'm going to talk a little bit now about modal trees. I'm sorry, I corrected this very messy. So this time we have a language that is expanded with 2 expressions, box and diamond. And an interpretation is a triple, where W is a non-empty set, R is a relation in W, and the interpretation function is a function from variables, from pairs, variables, and worlds to 2 truth values. The definition of conjunction, disjunction, negation is the same, though things this time are relative to possible worlds. And a box is gonna take value 1 in a world when A takes value 1 in every, sorry, it should be X, in every accessible world. And an argument is gonna be valid this time when no interpretation contains a world where all the premises are true and the conclusion falls in that world. This is the local definition of validity. So the nodes of our trees can be of 2 different forms. We can have a formula with a natural number, or we can have 2 natural numbers and the letter R indicating the accessibility relation. The initial list will record the idea, the assumption that there is a counterexample. So we write all the premises in world 0 and the negation of the conclusions in world 0. And the tree rules for the classical connectives are exactly the same, although you will have to carry the natural number along. And for the modal cases, we have that if we count with information that box A is in world N and the information that N has access to M, then we have to write A in M, and we have to do this for every such M. While in the case of box AN, with this information, we have to introduce 2 nodes. The node that N are N, where M is a new a number not in the branch, and A is true in M. And of course, the closing conditions tell you that if a branch has a formula and its negation in the same, followed by the same number, then that path is closed. So here a very basic example. So here we are triggering the rule for the diamond. So we introduced a new world, and then the disjunction, what comes after the diamond in that world. And here box negation Q 0 with this node gives you this, which closes this branch, and box negation pin 0 with this gives you that. Now there is a variation of the modal trees which have some interest in the philosophical literature, and is the idea of a supervaluation. So as you probably know, at least in the case of vagueness, it was very much discussed, the supervaluations theory, let's say, right? And basically, you can read the modal semantics in a supervaluationist way. So each possible world is a precisification, etc. And the only difference between supervaluationism and standard modal logic is the definition of logical consequence. So for the supervaluationist, that a sentence is true means that it takes value 1 in every possible world. And so we have to adapt the definition of logical consequence. If you remember, our previous definition said that a counterexample is an interpretation with a world where all the premises are true and the conclusion and one of the conclusions false. In the case of what they call global consequence, an argument is globally valid when no interpretation assigns value 1 to all formulas in every world and value 0 in at least one world, for every formula in at least one world, right? So basically the idea is that a counterexample this time is an interpretation making all the premises super true and all the conclusions not super true. These two inferences are globally but not locally valid. The first one is the box introduction. It is not exactly like necessitation. It's like the inference version of necessitation. And this inference here, which is the comma version of excluded middle, right? So the supervaluationist accepts that A disjunction negation A is valid, but does not accept. So the meaning of the disjunction and the comma doesn't match, right? Now we can easily adapt our modal trees for the global case by using the following trick. So our initial list, instead of a possible world, will feature G indicating like a universal modality, right? So this time what we want is that each premise in the argument is globally true, so true in every world in the interpretation, and each conclusion of the argument is not globally true, so false in at least one of these worlds, right? Of course, this global modality follows the same rules as the box and the diamond, but in a universal way. So you don't need to mention the accessibility relation. So this modality has a universal access, yeah. And the closing conditions are the same as before. So let's have a look to a couple of examples. The first one is that A disjunction B does not imply A comma B in the case of supervaluationism. So we write the premise, we write the conclusions with a negated modality. And the thing here is that each of these different conclusions will give you a different world, right? And then you discharge the disjunction in each of these different worlds and you will have one path open to the counterexample. So even though so the fact that A disjunction B is globally valid does not guarantee that one of the disjuncts is, okay? And the second example is the box introduction rule, which goes like this. Okay, so I think I will finish in 5 minutes, so don't worry. Oh, five, a bit more perhaps. So the final thing I would like to discuss is meta-inference validity. So we have these ST and TS notions of logical consequence. We see that it is interesting to look at the notion of a meta-inference, but actually it is not completely clear what is the proper, if there is any, the proper understanding of meta-inference validity. So there is some discussion here. The notion we used for our trees is actually known as the local notion of meta-inference validity. The idea is that what local meta-inference validity does is preserving satisfaction in each valuation. But if you reflect, I mean, if you think about it, I think that this is not really what we mean when we consider the validity of a meta-inference. If you think on an analogy between meta-inferences and inferences, in the case of inferences, it is truth or satisfaction that is preserved from premises to conclusions. I think it is kind of natural to think that in the case of a meta-inference, it is not satisfaction what should be preserved from premises to conclusions, but validity. Okay, never mind. I think that the global definition is, at least if you compare the local and the global, is conceptually somehow better motivated than the local definition. The global definition tells you that a meta-inference is globally valid when, it's globally valid whenever, if the premise is valid, the conclusion, so the inference in the premise is valid, the conclusion is valid. Now this notion of validity actually is not very nice. Now the problem is that in this definition, there is no connection. So when a meta-inference is globally valid, there is actually never a connection between the premise and the conclusion, in the sense that if a meta-inference is globally valid, this is because either the premise, the inference in the premise is not valid, or the inference in the conclusion is valid. But actually, whenever you have a meta-inference that is globally valid, so if you assume that this meta-inference is globally valid, this is because either A arrow B globally implies anything, or anything globally implies C arrow D. So it is not a very, let's say, very useful notion of logical consequence. I propose a different notion of global validity. Dave told me, don't call this global because you're gonna confuse everyone. But well, let's call it P global for Pablo, or proper global. So the idea is very simple. Instead of considering validity, what we are going to consider is sets of valuations, right? And for each set of valuations, we will see that if in that set of valuations, a global consequence is present. So if the premises are satisfied by all valuations in that set, then the conclusions are satisfied by all valuations in that set. Of course, this looks very much like the supervaluationist thing, but at the level of meta-inferences. And actually, you have these two things. So generally speaking, the key global consequence will match with the local reading, but very much like in the case of supervaluationism, not when boxes are around, not when multiple conclusions are around. And in particular, the meta-inference this time, yes, corresponding to the necessitation rule, is globally but not locally valid. And this meta-inference, I don't know how to call it, like validity excluded middle or something like this. This meta-inference is locally valid, but not globally valid. Of course, I think this is the right thing to think, right? Not that any formula for any two pairs of formula A and B, either A implies B or B implies A, that makes no sense at all to me. So I think this is the right thing. I'm done. You will have to read the book and perhaps to learn Spanish. Thank you.
I'll stop the recording here so I can have them separate.
There's